Let's start off the chapter with something a little bit more familiar. This is an old question, MJ08 paper 4. Now you have a small rectangular coil that has 140 turns of wire. Ooh, they should label that N already. N for the number of turns. Will be useful later. The sides A, B, C, D are length 4.5, 2.8 as shown. They didn't give us the poles of the magnet, huh? Never mind. Okay. So the coil is held between the poles so that the coil can rotate about an axis through the center. The magnet produces a uniform magnetic flux density through the poles. So I guess if they never told us, we can assume lah. Okay, for simplicity of mind, we assume there's north here and south here. So you got all kind of what you call this, magnetic fields going from left to right. And that's your B. I'll just draw one. There. Just for us to know. When the current in the coil, so we are sending a current in the coil. Is this induction or force on conductor? Nah, they give you electricity ma, so this one is current. Oh, so it's like force on conductor from magnetic fields chapter. So maximum torque in the coil is 2.1 times 10 negative 3. Where on earth did torque come from? Scratch your head a little bit. Can you imagine this coil turning about an axis? Let me show you the idea. It's based on how DC motors work. And DC motors generally is like this. You connect some circuit to a coil in a magnetic field and it will start to turn. So you see how there's a force up and a force down as well. Okay, so that's a direction of current, this green arrow here. And so because there is current in the conductor, there will be a force on conductor and there will also be a torque. Remember what torque is from AS, okay? Forces, and in fact these two are couples, torque of a couple. So same magnitude but different direction. So this is how a motor works. You put in there, it will turn, and this turning coil will rotate a wheel or toy car or whatever that is, or fan. Okay, so that is how DC motors rotate. And they told us the maximum torque. So for the coil in the position for maximum torque, state whether the plane of the coil is parallel or normal to the direction of magnetic field. How do you brain this? Okay, time for some drawing time. So it's a bit, if you can't see it straight away what the answer is from just staring at this diagram, it's good to learn to redraw or think in different perspective. So for example, maybe I say I want to see this setup from the front view, like where this eye is looking. See this eye? Alright, so we're going to redraw some of this thing. So front view, you will see coils, which is here, AD, right? And also, don't forget the magnetic field, which is going in generally. If we define north-south, then in this direction. So what about current? Let's choose a direction for currents. This question doesn't really care much about direction, so you can just assume, alright, maybe current is flowing in this direction. And here. How about that? Okay. So what is happening here is that in AD, current is flowing into the page here, put X. Okay, that is this part. And out of the page on the right. So we're going to put a dot. Remember how to do this from the previous chapter? So where will the force be pointing? Take out your Fleming's left hand. Point your pointing finger to the right. Middle finger into the page at A. So you have a force downwards. Oh, okay. So you have force. And the other one, point to the right. But middle finger is pointing at yourself out of the page. So the force will be upwards. So then this force will cause this whole coil to twist about the axis. And the axis is in the middle, which is right here, this orange dot. Okay, so that's the torque. Is this maximum torque? Yes, it is. What does it mean by normal leh? Okay lah, for fun we draw also. So what happened if your coil is now normal or perpendicular? So something like this. AD. Okay. So at A, into the page, at D, out of the page, for example, where will the force be acting? Down. Huh? Down? That's so weird. What is this? How about the one down there? Out of the page, up. Huh? How are you going to have torque like this? It's not going to work, eh? So you can see how there's no maximum torque here. I mean, there's not going to be any torque at all. But maximum torque will occur when your plane is parallel to the field. So we're going to say that down in our answer. Maximum torque happens when? Parallel. So you can say plane of coil parallel is the keyword to the magnetic field. Or I'm using a shortcut and say B field. So 1 mark for parallel. That's B1. Okay. Now we have to calculate the magnitude of the force on the side AB of the coil. Where is AB? AB, AB. Oh, AB is here. This part. So what is the force acting on side AB? How can we calculate it? Force on conductor. Maybe some of you say, Miss, we learned before, right? F equals to BIL sine theta. Okay, let's try and see. BIL sine theta, we can find or not. So we say, let's find force on AB. BIL sine theta. Do we know B? Wait. They didn't give us B. No B, how to calculate? Cannot, eh? We don't have enough information. Oh, no. They only told us, it's a flex density B. That's all. They didn't tell us what value. So, unfortunately, good idea, but I don't think we have enough information to use this yet. So, no. Cannot use that. Then how to find the force, miss? Hey, calm down. They gave you torque, right? Remember, just now we draw the torque. So, if you have the rod, which is like that, okay, and you have some force acting on it. So, maybe down here is force along AB. Then this side is force. What's the other one? CD. What is this? A to D. Okay, AD. Point A to point D. And let's say you have some current flowing through it. Can you find the force if you know the maximum torque? Remember from AS? Torque equals to force times perpendicular distance, or perpendicular force times distance. And this one is maximum torque. We know the maximum torque, so we can calculate this. So maximum torque is given to us, and that is 2.1 times 10 negative 3. Then what to use for force? Remember, very important. This is a torque of a couple. So which means I can just take any one side of the force, multiply by the distance between them. So the distance between them is the whole length of the rod, and that is going to be 2.8 cm. From one end to the other end. Torque of a couple, remember from AS, okay? So we're going to write that in 2.8 times 10 negative 2 because centimeter. And we should get a FAB of about 0.075 Newton, very small. Okay, 2 marks. Where does that come from? One from you substituting the correct equation. You knew that torque equals to force times distance between these two couple. And of course, final answer, 1 mark. Wow, to think of force on conductor, now it's turning leh. Yeah, you do your left hand rule and adjust lah. Now we come to the next part. What is the force on side BC of the coil? Where is BC? BC? BC is down on this end. Is there a force acting on it? If you're not sure, redraw. BC, okay, so BC will experience a current this way. So let's draw BC out. First thing, you have your magnetic field. Pointing to the right, let's say point to the right. All these are arbitrary, you can define whichever direction you want. And of course, this is section BC. Then, the current is flowing in this direction. Do you see something funny here? Will there be a current, my friend? Remember your force equation, BIL sine theta. What is theta? The angle between B and I. Is there angle between B and I? No. So there is no force. This is sine of 0. So this is 0. So you can just say 0. Or you can write 0. 0, 0, 0 everywhere. So that's just 1 mark for 0. Okay. Next. Use your answer in B1 to show that the magnetic flux density between the poles of the magnet is 70 millitesla. Remember just now we said we don't know the B, we cannot calculate. Now they ask us to find the B. But we need to use our answer. This is an important clue. Whenever you see these guys, use the answer from the previous section. So B1, what is B? What do we find? Oh, we found the force AB. That gives me a clue. So if I know the force AB, now I can use BIL sine theta. Yes, I like it. Let's try it out. So redraw once again. Magnetic field. Where is our wire pointing this time? You can call it this way. So this will be sides A and D, I believe. And you have, just now we found the force AB. And of course another force here, which is the same magnitude. And this force is due to a current either moving into or out of the page, well, into the page in this case. So that will be that. So we know the current, we know the force, we can find B. So let's write it down. 0.0, what was 0.0? 0.075, correct. Equals to B, we're trying to find current. You got to tell us current, right? 170 mA is right there in the middle of all the words. 170, so we write that down. Over here. 170 times 10 negative 3. That's for milli. What else do we have to write? Length. What is the length of this thing again? Be very careful. You might be tempted to say, Miss, this one is 2.8 cm. So we use 2.8 cm. Wait. The length of conductor is like this. Whoa. This one is 2.8 cm. This one is 4.5 cm. The force is acting on this part because of a current moving through this part. Be very careful. This side, yes, it's current, but it's parallel to the magnetic field, so no force. So be very careful which side you are looking at. Rewind back to your force on conductor from the previous chapter a bit. So the length here, we are using the 4.5 cm because that is the part where we are looking at how, this is what, length AB, right? My diagram, yes, AB, force on AB. And that is what we're going to plug in here. So let's continue calculation. 4.5 times 10 negative 2. Theta need to put or not? What is theta again? Theta is the angle between currents, which is this current, and the magnetic field, which is in this direction. So it's perpendicular, 90 degrees, so we don't have to worry about that. Or you can tell that from here, into the page and then to the right, perpendicular, so okay lah, no sine theta. Now you calculate your B. So your B here, you should get, I already pressed calculator for you, you should get about 70 times 10 negative 3 Tesla. But wait, there's something funny up with this setup. Firstly, if you actually press the calculator, you will realize that what I wrote there does not equal to 70 millitesla. I got check or not now, you just watch me only. So, something is missing because if you get this, you realize that your magnetic field is actually much bigger, which is not correct. So something is missing here. Now you look at this, FAB, force on AB. That is the force on one single conductor inside this this square loop. But what actually is happening is, if you look carefully at the diagram, there's actually many loops. Look, many coils. Why? Because n turns of coils. So you need to like, oh, it's not just one conductor, there's actually many conductors. So it's not just AB, but one round of AB, round 2 of AB, round 3 of AB, round 4 of AB, and every single round will experience a force, which is AB. Okay, I think of it, if I stagger it out like that, many layers, you zoom in, every single conductor, every single rotation got its own force. So there's a composite effect there. So what we really need to do is tweak the formula a bit. Force on AB section, yes, but there are many conductors there because of the many coils. How many turns are there? N equals to 140. Oh, I'm having disappearing words again. So 140 turns So that means this must be NBIL sine theta. And of course, that's because there's many turns of a coil. So remember, if these are coils, be a little bit careful. It's not just one coil, many coils. So the force is many times larger. So we need to tweak our formula a bit. Here we must multiply by 140 also. Now we press calculator and check. Now you will get 70 millitesla. So 70 times 10 negative 3 Tesla. Okay, so remember BIL sine theta, yes, correct, but that's for one conductor. If you have a coil, there are many conductors there, and you must take into account every single one of them. All right, next question. In case you haven't memorized it, it's a good time to practice memorizing. Remember the key word or the key equation, that is EMF proportional to change in magnetic flux linkage over time. Or a better word is rate of change of magnetic flux linkage. So we're going to say that the induced is a pretty important word. Others are like, where the EMF come from? Okay, so induced EMF is proportional to what? To rate of change. That's a very important word. I would encourage you to use this instead of change in flux over time. Use rate of change. Of what? Of magnetic flux linkage. Sometimes in past year, this is 3 marks. Sometimes it's 2 marks. So it really depends. In this case, it is 2 marks for this. So 1 mark comes from, if you talk about EMF proportional to rate of change, 1 mark. And you mentioned magnetic flux linkage, another mark. Sometimes they will say proportional to, EMF proportional to something, rate of change 1 mark, magnetic flux linkage 1 more mark. So you go and see lah, okay? All the different parts here. Please memorize this. 3 marks for you. Now the current in the coil is switched off. And the coil is positioned as shown in 6.1. So back to original. Flat laying coil. The coil is then turned. Why can turn? You use your hand, you turn the coil through an angle of 90 degrees in a short amount of time. Calculate the average EMF induced in the coil. Where to start? Start with the equation. Stay calm. Take a deep breath. Remember, you are changing the flux. EMF is induced. But how is the flux changing? Wait, we write the equation first, then we will see. So you do know that the E is equal to, for now we don't need to think about negative sign. So usually we say D of magnetic flux linkage over time. How to find dN dt? No equation also. Well, here you're trying to find the average EMF. So what you can do is EMF, I usually write the curly E's, is going to be the delta N phi over delta T. And it's a good way to kind of find the average. So next question for you. What makes up phi? What's in the phi? Phi equals to, what are the possible things that can change? So you have BAN or NBA. NBA sounds nicer, like basketball. NBA sine theta. And you have to think about this. Among all these terms, what is changing when you're rotating? You say, Miss, the coil is rotating, so theta is changing. Yeah, theta is changing, but it's going to be very hard to calculate that here. So what we're going to do is find the average, right? So your coil is turning and turning. Average, Can we think of the initial and final? Because here we have a problem. Theta is changing non-stop. What theta to use? 0, 10 degree, 40 degree, 50 degree, 60 degree, 90 degree. We only know it go from 0 to 90. So how? Which theta to use? Can't use 90 just like that. So what we want to do is, we think about the average EMF. So instead of thinking about this thing, we say, we want to find the change in phi. The coil number is not changing. Magnetic field strength is the same. But the area did change in this amount of time. Change 90 degrees. Okay. How are we going to draw that out? Firstly, you have initial state. So we go back to this diagram, right? Where is it? This one. So if I look at the front view again, see the eye down here. Okay, I'm just looking at how this coil is going to move and rotate. In the beginning, initial, final, because we're going to look at delta, we're not going to look at the sign data because they're very hard to measure. So you have B. The coil starts off flat. Okay, then what happened? Then the coil here ends up after 90-degree rotation. So rotate up liao, become like this. Oh, I see. So think about the A in the diagram. When we say NBA, what's the A? A is the area normal to the magnetic field. So first one I want to ask you. Yes, this coil got an area. But is it normal to the magnetic field or not? No. So you can say here actually, the area that is normal to the or perpendicular to the magnetic field is 0. Don't have. The coil Then when the coil is rotated to be vertical, imagine the 3D is like that. Okay. Then there is an area normal to the magnetic field. Yes, this one is still A, but now area that is perpendicular to magnetic field got maximum, biggest, is largest possible area in this case. Yeah, you want to shade it out. Okay, we shade and see though. So where's the area? There, from here all the way to here. In the beginning, where's the area? Don't have this one only leh. It's only the wire, so not considered. So that is a change in area there from 0 to something very big. So let's see how we can calculate this EMF induced. So let's write it out. E equals to average delta. So we're going to do NB delta A. So N is 140, right? 140. Magnetic flux density B is 70 times 10 negative 3. Now the change in area. Gotta remember your coil is a 3D thing. So when we say maximum area is actually like this, and you have the flux coming through like that. So what is the area of this whole coil? And go and see the dimension earlier. Just now it's what? 4.5 and 2.8 cm. So this side is 4.5. Here is 2.8 cm. So from no area to maximum area. So the maximum area will be 4.5. So 0.045 times 0.028. This is in meters. Meter times meter. Okay. That is the maximum area. Divided by change in time. How long? 0.14 seconds. Okay, so we do 0.14. What do we get? Oh, if you pass the calculator, you should get 0.0882. So it can be roughly 88 times 10 to the 123. Oh, negative 3 volts. So 88 millivolts, somewhere there. Okay, so you see how we can kind of estimate the average induced EMF. We know in between the EMF will be different, okay, depending on the angle or the rate of change of angle. But we just say, okay, initial, final, that's the average, lor. So initial is 0. See right down here. Initial, there's no area. Final, got area. So that is what we call a change in flux, because flux depends on area. Wow, how to imagine this, miss? Let's stare at this simulation a bit. When the coil, you are rotating it with your hand, there's a change in area, but how do you see that? Well, you want to see area perpendicular to B, right? Nah. I try to align so that we are looking at B. Okay, do you see a changing area? Suddenly there's one point where there's no area, suddenly very big, very small, very big, very small, very big, very small. Why like that? Nah, because the coil is rotating. It's a 3D problem we're trying to solve. So you are trying to see what is perpendicular to the magnetic field. So that will be this. Hence you see an area getting big and small like that. Okay? So that's what we're talking about, changing area. Now some of you say, Miss, how about the angle? Just now you didn't include the angle. Well, the truth is, yes, if you look at the angle between, let's align it this way. The angle between the magnetic field and this plane or the frame is changing all the time. So you're going to have some kind of magnetic flux that's also changing all the time. We will learn more about this in the coming sections when we zoom in a bit more about how to think about the different cases. But for a first starter, let's look at this diagram. I found this a very good diagram to see about how to better think about change in flux and how that affects EMF. So, just now we already said, right? There's a change in flux. So I'm going to write that down. Change in flux, because why? We say got change in area. Yeah. But the change in area is related to an angle, rotation angle. So if you look at the side view, front view, your eyes is like that lah. Looking down, you see that the core that's rotating. And there will be a change in flux that you can see in this graph. So this is flux. Why cannot write one? Flux. How we calculate flux? B times A, or B dot A. So, how do we think of this? This will be BA. Depends on which convention you want to use. Sine theta? Sure. You want to cos phi? Also can. Up to you lah. But basically the angle is changing. And then you have this curvy graph because you are going around in circles. But what is interesting though is this EMF graph. So this is your induced EMF graph. Why out of phase one? What is going on? Stay calm. Remember the equation for Faraday's law? What's the equation for Faraday's law again? EMF equals to dn phi dt. And here's just a constant, so just en d phi dt. D phi dt, whenever you see all this d by dt, all these things, you should remember how to deal with rate of change, gradient, slope, area under a curve. So whenever we see E is d phi dt, then we should already ring some bells. Oh, that means this is also the gradient or the slope, gradient function of the phi t curve. So question for you, look at the orange curve. Where is the gradient the steepest, the largest change, the steepest gradient? Stare at it a bit. Okay lah, if you know how to differentiate, you're like, oh man, this one not very steep all here. So here is largest gradient, also known as steepest or largest change. So when this d phi dt is very big, that means your induced EMF will also be very big. So hence, at this point, you have the maximum induced EMF. Wow. So the biggest change means biggest EMF. Okay. Next one. Where's the other place? Here also got one more. This place is where also there's very steep, largest gradient by the different direction lah. Largest gradient but increasing, so positive gradient. Oh, here is negative gradient. Okay. So here, negative gradient but positive Emax. Then the other side, positive gradient. Largest gradient means largest EMF. So largest EMF down here but in the negative direction. Oh, so that is also thrown back to Lenz's law. E equals to negative. Oh, we didn't include the negative, that's why. So negative n d phi dt. So that's how Faraday's law and Lenz's law can be applied in graphs. Sometimes they ask you to sketch the graph. Sometimes they ask you to talk and explain the graph. But you need to know, remember, gradient of phi t curve is E, EMF. It's like what you all last time say. When I say, oh, look, you have a displacement time curve. Please draw the velocity time curve. And then I give you oscillation. Something like that. Oh, sorry. Not this one. This one. Please draw the velocity curve. How to draw? You gotta apply the same idea last time, okay? Like you gotta remember that velocity is rate of change of displacement, which also means the gradient of your ST graph. Back to kinematics, back to oscillation. But now you take the thing, apply in magnetic field. Because you're looking at the rate of change of flux. So remember, flux, EMF induced. There is a phase shift between both curves and you need to be able to think of how they relate to each other. Okay, for this particular case, let's just give them some names. This one is sine graph, sine something t. The other one is a cos graph. So the difference between sine and cos is 90-degree phase difference. That's why they're shifted. Okay, so that is all for this question. Just a starter to think of, wow, how to think of all these changing flux. What does it mean to change flux? Changing area is one of them. But we will look at more examples on how you can change flux, and of course, all the case studies of different ways. So that's all for this example video. A little long, cover a lot of stuff, but I'll see you in the next one.